Bismillah ar-Rahman ar-Rahim. We continue today on the last section of Unit 6, which is designing of any finite state machine or any custom sequential circuit. We're left off with the example of the sequence analyzer that will analyze the sequence, the overlapping sequence of 1, 1. So in any given sequence, if this is your input, it was named W, your output Z should go as 0, 0, 0. And then here, if you detect the sequence of 1, 1, the next bit of the Z should become 1. And then in this case, when you detect 1, 1, you get 1. And with overlapping, you will also detect this one as part of the next sequence. So your value Z should also become 1 for the next cycle. We took a look at the state diagram, and then from the state diagram we moved into the state table, which is here. This is the state table, and I brought it to this slide for a reason that I'm going to mention now. And from your state table, after that you give state codes to all the states that you have. So for state A, we gave it the code 00. For state B, we gave it the code 01, and for state C, we gave it the code 10. Meaning we need 2 flip-flops for designing our circuit, or 2 flip-flops minimum, because there are other coding techniques that you can use more flip-flops than the minimum. Okay, and then from state assignment, we change all A's to 0, 0, and then all the B's to 0, 1, and all the C's to 1, 0. So you rewrite the same table, but with the actual state codes. Since this is 2-bit, so we'll give this, the present state will be y1, y0, or in the slide they name it y2, y1. For the next state equation, we'll use the capital Y2, capital Y1. And from that table, you go on and get either do K-maps, or if you can minimize it right away. So you need an equation for Y2, you need an equation for Y1, and you need an equation for the output Z. Okay, so you make 3 K-maps. Each K-map is a K-map of 3 variables, which is Y1, Y2, Y1, and the input W. So you make 3 K-maps, one for Y2, one for Y1, one for the output. You get some equation here. And from that equation, you can draw your final circuit. Okay. Now, in terms of coding any finite state machine in Verilog, you can follow some guidelines to make the coding much easier for you. So we will divide the code into 3 parts. The first part is input and output declaration with any local wires or local rigs, since you're going to use behavioral modeling, so you need to declare the wires as rigs. You declare your inputs. Of course, you're going to have a clock for your flip-flops and a reset, either a reset or reset n, depending on the question. If it's a positive reset or a negative reset, or as we mentioned before, active high and active low, and your input W. And we have an output Z, and then declare any rigs that we have. In our case, if you go back here, we need local wires, which is Y2, Y1, and we need capital Y2 and capital Y1. Okay, so that's what we declared here, Y and Y. And then for your states, you have to write this line here. So this parameter will declare, will replace the value of any capital A that you use in your code with the code 00, B with 01, and C with 10. How to do that? Or how to easily do that? If you come up, if you go to your state table and you transfer this into the code table, which is here. So A is 00, B is 01, and C is 10. This is what you need to write in your parameter. Okay, so this will make your code much easier to write. Now this is part one, is declaration of the input and the output. Part two is right here. This is where you write your, actually we have four parts. So part two, this is where you write your next state combinational circuit. Next state combinational circuit. This will give you, or this will assign the value of y. The purpose of writing this code is to assign values of y. طبعا y is the next state variable. If you go back um, to this diagram, you see that capital Y is the next state variable. And all the next state have some combinational logic associated with it. So the purpose of this block is to write these values. Now, there are many ways to design finite state machine, but this is one of them. You can write this block directly from this state table. So take the state table next to you, and all you need to do is to transfer this information that you have in here in your code. So first of all, always add, since this is a combinational circuit, you're going to list the inputs of your combinational block. Come back to your diagram. You see that W is one of the inputs that's going into your logic. And also you have Y1, flip-flop Y1, and you have flip-flop Y2. So we have three inputs, W, Y1, and Y2. Sorry, small y1 and small y2. Okay, so here that's W, and Y is already declared as a 2-bit rig. فبالتالي I just need to write Y1. Or you can also write W, Y of 1, and Y of 2. This will be the same. So the point is, just list all the inputs of your circuit because it's a combinational logic circuit. Now, when you go into the block, you're going to use, depending on the value of Y, which is, and value of Y is the present state. Okay. Since this is a more machine, لا ما له علاقة بالمور machine. لكن Y case Y. Okay. Okay, I see what he did here. You can write the case statement in two ways. Either you write case, you need to concatenate Y with W, or you can make it case Y, and then inside your case statement, you check on the value of W using an if statement. Now, why we did that instead of this one? This way, it will make it easier to write or to read directly from the state table. So let's take it step by step and see how this code is implemented. طيب. So now, you write case Y, and you have three cases, either Y equal to A, or B, or C. So in case A, which is here, read this value out. So if W is equal to 1, what's the next state? Is B. And our next state variable is capital Y. So we say, in case A, if you are at A, if you are at state A, and W is equal to 1, make Y equal to B from here. Else, that means if W equal to 0, let Y equal to A. Capital Y equal to A. So if you design it this way instead of listing or thinking about how to list it in a combination of all the inputs, this is much easier to do. It's just reading out of your state table. And then case B, for this part, case B, that means you are here. If W equal to 1, my next state is C. If W equal to 0, my next state is A. So that's what we are writing here. So if you are state B, if W equal to 1, make the next state capital Y equal to C, and else, that means W equal to 0, make the next state Y equal to A. Same for state C, if if W equal to 1, make Y equal to C, and if W equal to 0, make Y equal to A. Okay. Uh, this default value is because we are only using 3 combinations out of the 4 allowable combinations. Since Y is declared as 2-bit, that means I can have 4 values for Y, or 4 different values for Y. So if Y is equal to whatever we did not declare here, which is case 1-1. So either you write default or you write 2-bit of 1-1. That's going to cover the same case. So default will just declare next state as don't cares or unknown. Actually, because we should never DH this value. It's not part of our state diagram. Okay, and then end case and end the always statement. Now, the third part is for the sequential logic. Since you already covered the combinational logic here, so if you come back to this code, sorry, if you come back to this diagram, now we already covered this part. We already covered this part inside our always block for the combinational logic. So what we have left is only writing the code for these 2 flip-flops. And these 2 flip-flops are easy. All you need to do is make the value of y2 equal to the value of capital Y2 on a positive edge of the clock. Also, don't forget to check for reset, whether it's synchronous or asynchronous, depending on the question. You need to take care of that as well inside your sequential circuit block. Okay, so if you come back here, that's what's happening. I will enter this block at the negative edge of reset n. That means I'm using an asynchronous active low reset. And of course, at the positive edge of the clock, first check for the reset. If you're resetting, now the value you write to the output of the flip-flop, which is small y, depends on your state diagram. Okay? Don't just go in and blindly say that y is equal to 0. This won't be correct. This will actually depend on your state diagram. So go back to your state diagram and you see that your reset is taking you back to state A. So in your reset statement, you said if reset n, or if not reset n, which is reset n equal to 0, make the value of y, which is the 2-bit output of our flip-flops, equal to state A. طبعا A is already defined as a parameter, so this will change to state 0, 0. ولكن if in your state diagram مثلا or in your state assignment you assigned that A is 1, 0. تمام? So this will take Y to state 1, 0. So to make yourself independent of writing the value of the actual states, that's why we use the parameter at the beginning, to make writing our code much easier. If you don't write this part, you can still make your code work. ولكن instead of writing A, B, and C, you have to write مثلا y equal to B, you write y equal to 2-bit of 0, 1. Instead of C, you'll say y equal to 2-bit of 1, 0. And it's easy to make mistakes this way. So make sure that you write this line for the parameter to define your state assignment. Okay, so back to the reset, we're going to reset to state A. Remember that inside the combinational always block, we use blocking assignments. And if you're using an always block with positive or negative edges, here for sequential circuit, we're going to use non-blocking assignments. Okay, so first thing, we're going to go in, check the reset. If you are resetting, please take me to state A. else that means I'm not resetting. All you need to do is to assign my current state should take on the value of the next state. Now, how this value of capital Y changes, this is what we already did in our combinational always block. Okay, so what I'm saying that is part 3 of writing the finite state machine code. This part will be always fixed. It's going to be the same code. All you need to take care of is what state are you resetting to, and if your reset is active low or active high, and if it's an asynchronous or a synchronous signal. So this else part is going to be the same. Just make my current state equal to the next state. في سؤال؟ Okay. Now we are left off with the value of Z, which is the output. Now Z is declared as an output. It's not an output rig. So if it's not an output rig, that means I'm not assigning the value of Z inside inside an always block. So I need to use the assign statement. So if you come back to your diagram, Z here is equal to Z is equal to Y2. Is this correct? Oh, so Z should equal to the state 10, which is C. So if you are at state C, okay, yeah, because we're only using, I see what he did here. So the value of Y2, which is this one, since I'm not using this combination and I will never reach it, so that means Z is equal to Y2 directly. You can make Z equal to Y2, أو يعني the general way to do it, Z should equal to state C, which is 10. But since Y2 will be only 1 at state C, that I can reduce, instead of using an AND gate with the value of Y2 and the value of Y1 inverted, I can directly just take the value of Y2. So anyway, for a Moore machine, the output depends on the present state. So Z equal to 1 for at state C. So in my assign statement, this is what I'm doing. I'm saying Z is equal to Y equal to C. So whenever my current state is equal to C, make Z equal to 1. Okay, this is part 4 of the code. Any questions? Okay. Another way to write this code. Now this code is exactly the same as the one in the previous slide. There is only one slight change. Instead of writing Z equal to Y equal to C, which was used in an assign statement, I will declare Z as an output rig instead of an output. So this way I can use it inside my combination logic block. So this part is the same. This part is exactly the same. And all the inputs and outputs and the parameters are the same, except for the change in Z. We made it an output rig because we're gonna assign the value of Z inside this always block. So instead of writing aside Z equal to small y equal to C, I just write the Z equal to without the assign. Okay, this is the only difference between this code and that code. Now, a third way to do it is to completely ignore, not completely ignore, I mean, you can just write it right away in one sequential logic block where you assign the values of capital Y. Actually, you don't need capital Y here. You can just write the input of the input of the flip-flops. So here we will assign only one wire for Y. We won't have capital Y anymore. So always at negative edge of resets and positive edge of clock. So we'll have only one sequential logic block. Now, if you if you go into the always block, first check for your reset. If your reset is active, make my current state equal to the first state that I'm resetting to, which is here state A. And then else, depending on my current state, now this block is exactly the same as this one, with a slight change of the value of capital Y. I won't have capital Y anymore. I'll just assign directly to the output of the flip-flop. And the most important point, most important part is that you use non-blocking assignment when you do that. The output is the same as what we did in the first version. Okay, now note that all these three versions are acceptable, and all of them will lead to the same design of the finite state machine. You might be asked to, in the question, to make separate combinational always block and sequential always block. Or if you were giving the choice, just do which one of these version is easier for you or makes sense for you. But you have to understand the code for all three. You need to know what's happening and what are the changes that you need to do. So for this one, for example, the most important part is to declare Z as an output rig because you're using it inside an always block. In here, what's important is that you use non-blocking assignment when you write your next state equations. Okay, so make sure that your assignment here is correct and that your code follows whatever version you're working on. Okay. Now we already have mentioned the design steps for state machine design in the previous class. ولكن let's go through it point by point. First, obtain the specification of the desired circuit, meaning what do you want from your circuit? For example, in the previous example, we want to create a sequence detector that will detect an overlapping sequence of 1, 1. This is the specification. It can be anything. And then from this specification, you write your state diagram. After writing the state diagram, everything here is systematic. You just follow the steps of the designs. But these two parts, you notice that this will be the most difficult part of your design. Most of you now are working on the project for 212. So if you have any design or any project idea, these two will be your most difficult part. How to transfer your idea from a description or a specification to a state diagram. If you get to the state diagram and you already draw the state diagram and make sure that your state diagram is describing whatever specification you have, everything after that is just systematic. Okay, so after you have your state diagram, write your state table. If looking at your state diagram, you have some reduction you can use, like if you get any unused state or states you'll never reach, you can reduce the number of states. And then from the number of states, you decide the number of state variables, how many states you need. And then choose the type of flip-flops you'll be using, either a D flip-flop or a JK or whatever. Write the state table. And then from that, derive the logic expression to implement the circuit using K-maps. After you get that, you can model your circuit in Verilog. Okay. Okay, the last example in this section is a circuit that will be used to swap the contents of two registers, register R1 and register R2, in response to input W. So basically what it means, I want to create a circuit to swap the values or the contents of two registers according to an input signal. If W equals 0, do nothing. If W equal 1, swap contents of R1 and R2. Now notice in this diagram, we have register R3. The reason we have register R3 is the same reason that you create a temporary variable in Java or in C or in whatever programming languages you used before. So let's say you want to swap, you have x equal to 5 and y equal to 2, and then you're asked to swap these two values. Now how to do it in Java, you're going to create an integer temp. I'm sure you did this before. You need to create an integer temp and you need to write x or temp is equal to x, and then x equal to y, and then y equal to temp. This is the only way you can swap two variables. Because from here, if you write x equal to y, the content of x now changed. You don't have access to this 5 anymore. This 5 is now 2. If you write x equal to y, this will make x equal to 2. And you will lose this value of 5. So the only way to do it is to declare a temporary variable that will be used for swapping. So first, save the content of 5 in the temporary variable, and then write the content of y in x, and then take the previous content of x and write it into variable y. This is exactly what we will be doing here. We have two variables, R1 or two register R1, R2, and I want to swap the variables between these two variables. So I either take R2, for example, and save it into R3. R3 here will be equal to will be similar to the temporary variable that I created here. So I'll take the content of R2 and save it in R3. And then next step is take the content of R1, write it to R2, and then take the content of R3 and write it to R1. So we have these signals. We have W, which is the input. This will decide if I'm swapping or not. And I have a clock signal. Do I need a reset? You should have a reset, either a reset or reset N. And then I have one output of my circuit called done. When done equal to 1, that means the swap is successful, or the swap is completed. Now this control circuit will have 6 outputs, 2 outputs for each register. One will tell the register to output its value to an interconnection network. This interconnection network is just basically it's a bus between all these registers. This is a bus. So this signal will tell the register to write the value to this bus. And this signal will ask the register to write the value from the bus to the content of the register. 6 signals because I have 3 registers. So R1 out, R2 out, and R3 out, and R1 in, R2 in, and R3 in. Okay. Since I have the specification of my circuit, I can go ahead and write out, I can go ahead and draw the state diagram. So our first state, which we'll be resetting to, is state A, which means no transfer. No transfer, meaning R1 out, R1 in, R2 out, R2 in, and R3 out, R3 in, all equal to 0. Don't write your value to the bus and don't write any values to the register. And you're going to stay at this state as long as W equal to 0, which is your only input. Now, if W equal to 1, move to the next state, which is do the swap. Now, the swap, as we said, or as we saw, consists of 3 steps. First, one of the registers will write the value to the temp, and then um, the second register will, or the same register will take the value of R1, and then R1 will take the value from temp. Okay, so I have 3 steps. That means I need 3 cycles to do it, and that's what's happening here. Let's take it step by step. Now, state B, I will make R2 out equal to 1, R3 in equal to 1. Meaning what? Meaning R3 will take on the value of R2. Okay, this is what's happening in this step. Now, regardless of the value of W, you can actually take that off. You don't need to write it. So after you are in this state, move directly to the next state, which is state C. What's happening in state C? State C saying R2 in equal 1 and R1 out equal to 1. What does it mean? Meaning R2 will take on the value of R1. After you're done, whether W equal to 0 or W equal to 1, go directly to the next state, which is state D. This will output the value of R3 and write it into R1. So R1 will take the value of R3. And this will complete the swap. So also at the same time, make my output signal then equal to 1. After you finish, just go back to state A. Okay. Now, from the problem specification, we wrote the state diagram. From here, we just go and complete the steps. Let's write the state table. I have 6 outputs, and all these outputs are more type outputs. Why? Because the output value depends on the state only. I don't see output values in going from a state to state. I don't see W equal to 1, make R3 equal to 1. Now, if you see something like that, this is a mealy type machine, meaning that the output R3, let's say R3 out, depends on the current state, which is A, and the value of the input. But since we only have values of the output inside the states, meaning I only depend on the current state, making it a mealy machine. Sorry, making it a Moore machine. So from the diagram, we need 4 states. How many bits? The minimum bits to represent those is 2 bits, which is log 2 of the number of states. So log 2 of 4 will equal to 2. So I need 2 bits to represent each state. Now, the next state, you can go to your state diagram and come up with these values. And note, once you are at state B, you will go to C regardless of the value of W equals 0 or W equal 1. Same for state C, you go directly to D. And if you are at state D, you go directly to A, regardless of the value of W. Only at state A, you're going to stay at A if there is no transfer requested. You're going to go to B if there is a transfer requested. Just read the value of the state diagram to find out these 6 signals, the value of these six signals. Let's take R2 out, for example. Go back to the state diagram and look for R2 out. So R2 out here is equal to 1. This is at state B. I don't see any other R2 out, so I go to my state table and set R2 out equal to 1 when the current state is equal to B. and so on. You fill all these values. Now writing the equations for the outputs, here it's going to be easy because you only have, if you check R1 out, it's only one at one state, R1 in, only one at one state. So all of them have only, it's only active at a single state. So for example, R1 out equal to C. Or you can say R1 out, if you want to write the code, Y equal to C. This is the current state variable. For example, R3 out, did I check R1 out? So R3 out is 1 when the current state is D. So I write R3 out equal to Y equal to state D. And so on for the 6. Not this is 7. So we have 7 outputs. Now the other equations you need to find out is the next state equation. Next state equation depends on this part of your table. So first move this into state assignments. So we're going to assign the value 0, 0 to A, 0, 1 to B, 1, 0 to C, and 1, 1 to D. Now we need to make k-maps to minimize the next state equation, y capital Y1 and capital Y2. So to do that, how many inputs we have? We have 3 inputs. We have the input W, and we have the present state. So each one will have a 3 variable k-map. Let's take Y2, for example. I want to fill the k-map for Y2. So I have here Y2 and Y1, and this is input W. No, relax. Sorry, I have W, and here Y2, Y1. Okay, that's 0, 0, 0, 1, 1, 1, 1, 0. And then this is 0 and 1. We start fill the table. Let's say we're filling for Y2. So the value of Y2 is right here. This is Y2 when W equals 0. And this is Y2 when W equal to 1. So for W equal to 0, we're going to read this part, which is 0, 1, 0, 1. So 0, 1, 0, 1. Then when W equal to 1, I have 0, 1, 0, 1. So 0, 1, 0, 1. Now to minimize Y2, I'm going to take these two. So capital Y2 will equal to Y2 Y1 bar صحيح or Y2 bar Y1 which is equal to Y1 XOR Y2. Do the same for Y1, capital Y1. Read these values and come up with the equation. This is what has been done here. This is the same equation that we get for Y2. And you do the same for Y1 and you get this equation. From this equation, I can draw my circuit. I'll first write the output expression as we did in the previous slide. This is the final circuit of the final sequential circuit diagram for the register swapping example. Once you have that, you go in and write your code. So for writing the code, actually all you need is this table, this one right here. Well, take this part and write it the same way as we did before. So if you want to do it quickly here, I'll write some of it and then we can move into the written code. So we will declare, we have input clock, input reset in, and input W. output. All of those are 1-bit output listed here. And then I need to create rigs for 2-bit rigs because I have two flip-flops for capital Y and small y. And don't forget the parameter where you're going to define A as 0, 0, B as 0, 1, C as 1, 0, and D as 1, 1. Now write your always block, the combinational always block. So always at either the current state changes or the value of W. Inside case current state, which is Y. So if I'm at state A, I will check the value of W. If W, which means if W equal 1, make capital Y equal to B. Else, capital Y equal to A. Case B, that means if I'm at B, check W. If W equal to 1, go to state C. Oh, actually, since W is not affecting the transfer from B to C, it's always going to C. So I can just write if you are at C, oh, sorry, if you are at B, the next state, capital Y equal to C. For C, the next state is D. And for D, the next state is A. Since I'm not depending on W, I don't need to have this if-else statement. Okay, now this is the end of your combinational logic block. Sequential logic block, always at the positive edge of clock, and let's say it's an asynchronous active low reset, so at the negative edge of reset n, check for reset. If reset n equal to 0, let the current state takes the value of A, which is the one that I'm resetting to, state A, else the current state will take on the value of the next state. End your always block, and then you need to write your assigned values of the output. So you'll go assign R1 out equal to the current state of C. So Y equal C. R1N equal to, if the current state is equal to D, so current state is equal to D, R2 out, and so on. Let's do R2 out, and then we can stop here. So R2 out equal to current state of B, so that's Y equal to B. Okay, now I have written this code here because it's easier for me to write the code while having a state table right in front of me. But if you go in and check the code, it's just going to be the same as I did. The combination circuit block will check on the value of Y and write this part. Is it the same as we did? And then the sequential logic part, also the same. And just define values of your outputs. Okay. Any questions?